here.
Okay, so welcome to the first afternoon session. And I got asked by the organizers to remind everybody, if you want to ask a question, please wait until the mic is there, because we have 100 participants, and then I can also hear the question and not only the answer, right? So sometimes it's more important to know the question than the answer. And now it's my pleasure to introduce Igor Pak from UCLA, who did some interesting work together also with Christian and Greta on defining what is a combinatorial interpretation, a very vague concept in mathematics. It's mainly example-based, and we now have a complexity theoretic definition of that, which is mainly due to Igor and his co-author's work. So this is great because we also have an application of algebraic complexity. And I'm now looking forward to his particular talk, which talks about vanishing of the Schubert coefficients. Please go ahead.
Thank you. Thank you so much for the introduction. And I'd like to thank the organizers for having me. And really, I'm a combinatorialist, so me speaking at this audience is slightly intimidating, but I'm very honored. Thank you. And thank you all for coming. This is what UCLA looks like. So I'm not very big on suspense, so I'll just tell you the main theorem right away. And that's my attitude. Basically, I'm saying we can do stuff. We can decide whether Schubert coefficients are positive in probabilistic polynomial time. And I'm sort of expecting you to be one of those guys, or maybe both. So most of you won't know what Schubert coefficients are, and even if you do, why would one want to do this kind of thing? Okay? I'm not going to poll the audience, so let's not get embarrassed. The plan of the talk is to kind of answer some of these questions. I'll tell you what this is about. I'll tell you why should one care, and by that I mean why I personally care. And I'll tell you later on how to prove this, which turned out to be a remarkably simple solution, which you will understand much faster than some other audience, and took me a long time and took the community a long time to do this. So let me start from the very beginning. If you have some kind of ring R with bases enumerated by combinatorial objects, I'm going to define structure constant in the way you would want to define them. Okay? Everyone okay with this? So structure constant. And then there are two main problems, really. The one that the one on the left is a problem that people have been looking for a long time. So often enough, these structure constants are actually non-negative integers, and what you want to know is to give a combinatorial interpretation, just like Marcus mentioned and I mentioned before. And but we're also going to consider a vanishing problem, or sort of dual is a positivity problem, whether those numbers are actually equal to 0 or strictly greater than 0. I hope everyone is okay. This is a very basic abstract nonsense. And so I'm going to start with a classical example. And by that, I mean little Richardson coefficients, which are structure constant in the ring of symmetric functions. If functions feels a little odd for you, just think symmetric polynomials in sufficiently many variables. So one can multiply two symmetric polynomials and then write down as a sum of other symmetric polynomials. And if those polynomials happen to be Schur functions, which you can see on the left, then you get some kind of non-negative integers. The reason they are non-negative integers is because those, the Schur functions are actually reducible as Gerian characters, and representation theory tells you that they have to be non-negative integers. And that's sort of introductory representation theory, and I'll even tell you what combinatorial interpretation look like. So this LR coefficient counts the number of certain tableaus in weakly increase in rows, strictly increase in columns, and they have a shape bigger partition lambda minus smaller partition mu, and the numbers written inside are the numbers which give weight nu. Okay, so there's only one more condition. If you read from right to left, from top to bottom, for every prefix of that word, it has to be a ballot word, meaning that if you sort of read 1, 1, 1, 2, 1, 3, until that point, number of ones was greater or equal than number of twos, greater or equal than the number of threes. So that's the whole thing. So this is an absolutely classical sort of foundational idea in algebraic combinatorics, that those numbers are not just abstract numbers. They count something. In this particular case, they count number of certain tableaus. Okay, and once you have that, you can prove a lot of results. Everyone cool with this? It's okay to say no. Seriously, go ahead.
If I'm less familiar with these sort of objects, is there any? So if I'm less familiar with these objects, are there simpler examples where you have some basis and then you can look at coefficients of some object in their basis and that counts something? Are there simpler examples?
Yes, there is a ton of simpler examples. They're just not that interesting. Mostly because they're simple. This is the one. In fact, it took, I think, I forgot exactly. Little Richardson stated this as a result, but they didn't prove it. It was a conjecture. They made some claims that they proved it, and it was proved formally only in about 79 or 80. It took because that's not super obvious. This is a difficult example, and that's what we care about, difficult stuff. Other questions at this point? Okay, so now I'll tell you where we're going. I care about two problems, both of which generalize little Richardson coefficients. The first one is Kronecker coefficient, which is just kind of the same story, but instead of irreducible GLN characters, you do reducible SN characters. Okay? In this case, you get some numbers. They were introduced and studied by Murnaghan back in '38, and it's pretty easy to see that in a sort of stable limit, they generalize little Richardson coefficient. So, so there is a way to basically say for each C lambda mu that it's equal to Kronecker coefficient with some slightly more complicated partitions. And they play a crucial role in geometric complexity theory. That's something I'm not going to tell you. Avi mentioned geometric complexity theory earlier today. And from the point of view of algebraic combinatorics, this is absolutely one of the two foundational problems. The second one is coming up, but for those of you who want to see sort of comprehensive list, Stanley wrote a survey where this problem was number 9 or something on the list. Okay. So the ones that we're going to care the most about in this talk is going to be Schubert coefficients, and so very important sign is there for a reason. And it's a little harder to define. I'll tell you, instead of doing a definition, I'll tell you a little more about this later. But they're actually older. They Schubert coefficients and Schubert polynomials in a sort of indirect way were introduced by Schubert back in 1880s, and then reintroduced and sort of developed from a very explicit combinatorial point of view by Laskowitz and Berger in the 80s. And they, to do one word, they represent the homology classes in complete flag varieties, and I know this may not tell you much. We'll get to more combinatorial description later. And in addition to being in Stanley survey, this problem is truly foundational. It's part of the Hilbert's 15th problem, and it really generalizes the following question. And that question, hopefully, we can understand. So suppose you have 4 lines in 3 space. It's a very basic question: is how many let's make sure that 4 lines are generic. Okay, in general position, how many lines are going to intersect all 4 of those? Yeah. Why?
Well, I just know it.
Okay, so see, it's very true. I don't know if I'm going to give you full credit for that, but
Trust me.
of course I do. Of course I do. But there is a reason why I gave this example. It's the same reason why everyone else gives that example. Is because it's the smallest case where this is non-trivial, where the number is not 1, but not 0, but 2. Okay. And but you can sort of see that if you want to have you can parameterize this new line by 2 numbers where it is on the first 2 lines, and then there is one constraint coming from being intersected with the 3rd line, one constraint coming from the 4th. So the number should be finite, and Hilbert's problem basically asks to make this rigorous. That it actually does not depend on general position. And what does that even mean? Okay? Being general position will come up. So here is a slightly longer but still completely combinatorial description of Schubert polynomials. So what we do, it's a sum of the monomials. The monomials, summation is over certain tilings, and each monomial corresponds to a product of some variables xi, and you can sort of see that with tiling this kind of staircase shape, where vertically we wrote a identity permutation, horizontally we wrote the permutation for which we're doing the polynomials, and the curves connecting 1 to 1, 2 to 2, and so forth. And the curves are doing the permutation, and now the intersection squares are the one that's giving you variables in the polynomials. So anyway, the point is there is a completely combinatorial description. There is one more condition that I didn't mention: no 2 curves are allowed to intersect twice. But that's all there is. The problem is, once I define it that way, it's completely unclear why one would want to study this at all, and that's because this is not a definition, that's a theory. Took a long time, over 20 years, until people came up with those pictures and figured out how to write Schubert polynomials in a form that combinatorialists can understand.
What is RC standing for?
RC graphs. That's what they're called. Normal people call it pipe dreams, but that's a notation that's stuck. They're called RC graphs. I think it's row column.
Row column.
Yeah. This is a notation introduced by Sarah Billy and Nantel Bergeron in 2003, I think. Around 2000. Okay, so anyway, I'm okay if you didn't follow this at all. So let me tell you kind of my life goal as to basically show that these numbers do not have a combinatorial interpretation. And it's been a long time. If you, but even now, if you open any standard paper or book on the subject, they're going to say, oh, it's a famous open problem. But people don't try to solve famous open problems, really, not really. They sort of they're okay with with those problems being unsolved. And I don't know if it's me being Russian or my age or my tenure, but I kind of want to solve that. Okay, so that's what I want to do. And now I'll tell you a deeply personal story. I mean, not that deeply. So basically, I didn't want to do complexity theory. That's not what I wanted to do. I wanted to make a very narrow notion of what combinatorial interpretation is, and by that I wanted to say that combinatorial interpretation is a number of integer points and a nice polytope. a nice convex polytope, and that and little Richardson coefficients do have a combinatorial interpretation of that kind. So you would think that this would be the right notion. And after writing, I don't know how many papers on Kronecker coefficients and integer points, basically we concluded that no, this definition doesn't work at all. Doesn't make any sense. That's mostly because when you have integer when you're accounting integer points and polytopes, you can do magic, total magics. For example, the theorem just shows that even in 3-dimension, counting number of integer points and the projection of the difference of two polytopes can be Sharpe complete. This is really, it's somehow integer points don't feel convexity as much. And there are various ways, we have even fancy ways to phrase that, but the moral is it's just a wrong definition. It's, took me a long time to basically conclude that one should just go big. So Sharpe is the right definition. And therefore, for a while, we started doing proving results of what is not in Sharpe. And it's very hard to prove those results because there were not that many tools to deal with. So we had to invent those tools. And turns out, and what we learned, I'll show you some results on this, that the vanishing problem is really the key to understanding what's in Sharpe or not. And that's what we learned from all the tools that we discovered. Is everyone clear about my life goals? Yeah. Okay. So the whole story of complexity side of the story really started with our joint paper with Christian Nickenmeyer, and you can just read the first line of that. So if you take a number of satisfying assignment for F is the number of satisfying assignment for this formula, G is the number of satisfying assignment for that formula, subtract, take a square of the difference. That actually is a very nice counting function. It's non-negative, it's in gap P, except it's not going to be in Sharpe for a good reason. And that's because the positivity problem is saying that this number is actually different from that number. You shouldn't be able to do it in the polynomial hierarchy, and you can, because that's the vanishing problem becomes C equal to P problem and so forth. And we can do it for lots of other polynomials, for general inequalities given by defining semi-algebraic set and so forth. Really, we developed, this is, Fox only publishes like 12 pages out of 82 that we wrote. This is a monstrosity of a paper, and I strongly encourage you to read as many pages as you can handle. In a sort of more standard kind of clean result is, remember, we're going to algebraic combinatorics. We showed that the square of a character is not in Sharpe for a similar reason, and that's because deciding whether the decision problem whether character 0 is actually C equal to P complete. And that already resolved some problems in algebraic combinatorics, showed that certain things are impossible, and people started to get worried that the whole problem might have a negative solution. Until that result, they didn't think they will ever see such thing. Okay? And I want to mention one final result of this sequence. There is a fundamental inequality called Alexander-Fenhoff inequality on mixed volumes, and we were able to develop a somewhat more complicated tool that doesn't fit into examples above to show that Alexander-Fenhoff inequality cannot be proved by combinatorial method, even when even when polytopes are really ordered polytopes of posets, so that the volumes is the number of linear extensions. And in this case, again, we were able to show that this is that the defect is the difference of two sides. So the defect of this inequality is not on sharp P because equality conditions for this inequality is not in the polynomial hierarchy. That's what we did. I know it's a lot of results, but the point is here is sort of life goals updated. What you want to do is to show that Kronecker positivity and Schubert positivity are not in the polynomial hierarchy. That's the conclusion of this. Okay? Everyone clear about my updated life goals? Okay, so this is why for Kronecker it's wide open. We don't. I don't know how to do this at all, and I'm sort of. I don't really have tools anymore. I used to think I have tools, and so the best result on this is Ickenmeier and Müller-Walter, who showed that Kronecker positivity is. It should have said NP hard. I'm sorry, the problem that I have now sort of comes from the fact that very recent theorem by, let me not say them all, by Bravo et al., who showed that Kronecker positivity is in QMA, and that shows that the tools we developed previously cannot be used in principle. One needs more tools. The one which would survive going to quantum. Okay? Everyone okay here? Okay. So now that now we're going back to Schubert positivity, and that conjecture is false. You could have remembered that from the first slide I showed to you, because I showed that this can be done in probabilistic polynomial time. So that is completely false. And that's what the talk is about. And in fact, there were a couple more conjectures that were made in recent years when people started to look hard at Schubert positivity, and they're all false because it's all in probabilistic polynomial time. Okay? So this is me saying what we did is important. Okay, so let's see. So now time came to for me to tell you what Schubert positivity is in a slightly different way. And here is I spend a lot of time trying to figure out a linear algebra version of that. And here it goes. So we're given 3 n by n integral matrices. And we're looking at complete flags of length n. So these are sequences u0 inside u1, inside u2, etc., up to un. Okay, so sequences of subspaces. So ui has dimension I. And now and then we have a whole bunch of conditions of what are the dimensions of intersection of some of these spaces. Okay. So and those look innocent, but really they generalize the idea that we're looking at at line which intersects 4 lines and has some dimensions of intersection. That's a generalization of that notion. Okay, so there's no need to look very carefully, but once you state it that way, this is a problem, a purely linear algebra problem. Okay, except you cannot solve it that way. Go ahead.
What are the EJs here?
Oh, that's a coordinate flag.
Oh, the coordinate flag.
Yeah, that's that E1, E2, E1, E2, E3, and so forth. Okay. So the first part showed that this is a linear algebra. This quote I like. So Knudsen is saying that vanishing is actually very important for real life. I'm slightly dubious about that, but not because I know anything about engineering, but because I'm not actually sure anyone in the field knows anything about engineering. He might have Googled heavily. So the point is, Schubert positivity important, and some people think it's important in real life. So let's go back to, remember I told you, Schubert positivity generalized Little Richardson positivity. So let me give you some background on that. And there is a famous essential observation by Delaire McAllister independently. It's because the papers appeared on the archive within 1 day from each other, even though the publication time took a while for the second paper. So really, the first part is Little Richardson coefficient, the number of integer points in certain polytopes, called Gelfand-Zetlin polytopes. And the second part is the Knudsen-Tau saturation theorem. Let me show it to you even bigger. So that's a saturation property. We're saying that let's take n equal to 2. So Little Richardson coefficient for 2 lambda 2 nu greater than 0, then Little Richardson C lambda mu nu is greater than 0. Since this is a number of integer points and everything scales, the whole problem becomes a problem whether there exists a rational point in a polytop. Since polytopes are defined over rationals, that becomes a linear programming, whether polytop is empty or not. So basically, everyone wanted to generalize that, and I'll tell you in a minute. But before I do, let me mention Burgess and Meyer paper, who shows that you don't need to use big guns. You can use sort of go through the original Knudsen proof and do quite a bit of work to turn the problem into network flow problem, and then it can be solved much faster, actually. So unfortunately, the saturation property is just false for Schubert coefficient. We discovered it relatively recently, and there is something to be said about, so this was people kind of believed it because this was conjectured back in 2004. But there is something I learned about really old conjectures. They had really old computers. They didn't check them. So the counterexample is for n equal to 4. It's not really that far. You don't need to, I mean, our papers, one paper proved one counterexample for one direction, another one for another direction. But really, and we constructed infinite families, and we did a lot of work. But really, you could just prove it for by looking at all triples of permutation of 4 elements. This is not that hard. So this is a long slide, which I don't want you to read, which basically says special cases of Schubert coefficients have been heavily studied, so heavily each of those will require a separate talk. This is a fundamental problem. Okay, so here is our result. I'll say it once again. So you really can stop at the first line. So Schubert coefficient is an RP. Schubert positivity is an RP. And but it's sort of good to compare. So for permutations on n letters, it's basically n to the 8.75. Where 8.75 looks good, but really it comes from 4 plus 2 omega, where omega is a multiplication constant. This can, in principle, go down, just not soon, maybe. So that's our result. Everyone clear? Once you see our result, you can sort of maybe figure out where this is going. RP doesn't come from nowhere, but I want to mention that this 8.75 is actually comparable to what you get without Bürksen-Eichenmeier network flow algorithm. If you just use standard ellipsoid algorithm or interior point algorithm to solve little Richardson positivity. So even in this tiny special case, the algorithm is quite comparable. I hope he enjoys his dream. So we basically conjecture that RP is the best one can get, that Schubert positivity is actually not NP. And I'll tell you what this mystery box is. You can kind of figure it out. But before I do, let me mention another really simple special case of so there is an analog of Schur function which corresponds to symplectic group, where instead of the usual characters, you get projective or spin irreducible characters, symmetric group, and you can do exactly the same thing you did for Schur functions. Okay, just everything, the whole story exactly works out the same way. However, saturation fails in this case. Everything else works out fine. The structure constant, the number of certain tableaus, the number of integer points and polytopes. But if saturation fails, there are no other tools. So basically, this was open for the longest time. If this can be done in polynomial time, and if you want deterministic answer, it's still open. But a tiny corollary from our paper saying that yeah, it can be done in probabilistic polynomial time. I still believe the conjecture. It should be possible to do it in deterministic polynomial time, but we just don't have enough tools for that. So even if you go away from little Richardson to a tiny little bit, it's still going to be hard for you. So basically, this picture is representing the truth. Colleen Robichaux, my co-author on this paper, came to work with me as a postdoc, and we spent 2 years trying to do this. Go ahead.
On the previous slide, so what is Schur P positivity?
So there's analog of Schur functions called Schur P functions. They lie in, so this pi are power sums, and there is like a parallel theory of that. And in fact, there's even a book just on Schur P functions by Humphreys and somebody else. Basically, everything works out from algebraic combinatorics point of view exactly the same, except complexity doesn't work.
Mm-hmm. And then in the two lines, the conjecture says it should be in P, but what you showed that is in RP.
Yeah.
Okay.
Yeah, we're very close.
Yeah.
Still not enough. I mean, yeah, it might be my conjecture. I'm not 100% sure. I call it folklore conjecture because people, after the whole Knudsen-Tau saturation, people looked at every single thing very carefully, and they conjectured everything about everything. So we spent 2 years trying to prove what we now know is false, that Schubert positivity is not on pH. And it's frustrating to try to prove false conjecture, if you're honest, obviously, and didn't work out. So let me tell you what actually happened. Told you it's a personal story. So the first thing we did is we realized that Schubert coefficients is in AM, assuming the generalized Riemann hypothesis. It sort of becomes a matter of faith if that means that it's in the polynomial hierarchy at all. And I think Robert is not so sure. But we believe that that's it. That disproved the conjecture before, so I believe in the generalized Riemann hypothesis. So that was very close to what we wanted. That was already kind of amazing from my point of view, that we could do that. Then in the next and the progress started coming very rapidly. We cleaned up the proof and made it better, work for all types, so including symplectic group and orthogonal group. But then we realized something else. We realized that it's actually in AM intersection with co-AM. That was an even bigger surprise. I sort of didn't think I would live to see that. And then a few months later, we proved that it's an RP without any assumption at all. So that's how it went. It went from basically nothing, from being in P space down to RP in a matter of months. Everyone okay with my personal story? Okay, so what did we do? Luckily, you already heard a lot about Hilbert-Nussdalen. Let me not repeat that. So let me just show you the slides that you already seen. So that's where that's what we use. We use coherence results that Hilbert-Nussdalen is in AM, assuming the GRH. Can I move on? Can you tap him on the shoulder? Okay. Everyone okay with this? Okay. So unfortunately, that was not enough. We needed a parametric extension. The reason it was not enough is you remember the word generic for the 4 lines that I used. That makes everything hard. That's the main obstacle, and so the parametric. So we needed a parametric version of Hilbert-Nussdalen Satz, which means that the coefficients are some kind of Laurent polynomials, and then we're looking at solutions over the algebraic closure. And luckily, just in time for our work, there was a paper which showed in a roughly similar way, but with a somewhat different proof, sort of using the fundamental coherence fundamental idea that this extension of HN is also in AM, assuming the GRH. Okay, and that's what we needed. Okay. So now I can start putting things together. So essentially what we showed is that Schubert positivity is an instance of H and P. And now that you're looking at it, you're staring at that, this is not a surprise, but it was a surprise for us. We didn't think this would be possible. And essentially, we didn't have to work super hard at all, because there are people who work in to do symbolic computations in Schubert calculus. So they came up with a nice system which worked for us. So we just took their system, literally took their system, observed that there has to be some work to be done to realize that this becomes decision problem for that is an instance of H and P, and we're done. Told you, it's really easy. Okay? Everyone okay with this? So, and this might look like a super easy approach, but in fact you can do all kinds of magic with that. So this is one paper that we wrote, sort of generalizing Schubert coefficients further, and I will never tell you what Gromov-Witten invariants are, and this is not super important. This is counting curves of certain degrees. intersections of curves of certain degrees. Complicated. But the point is the decision problem, whether there exists at least one of those, is an AM assuming the GRH, and for that one, you need to generalize H and P a little further. To be precise, you need to allow exponents in the polynomial to be also variables. But it all can be handled. Very similar proof to the original one. In fact, there is not the reduction is not super hard. And once you put it together, you get the result for Gromov-Witten invariance. You do not get AN intersection with co-AM. You get just AM. Okay? And that's where we come to the second, our second approach. And there is a little bit of a mouthful. So these are notations that I'm using. So Bn is upper triangle matrix. I'm simplifying them. The way it's written in the paper is all root system stuff. But this is all for root system A. So suppose UN is just upper triangular matrices. Vn is a vector space of upper triangular matrices with zero on the diagonal. That's an ambient space in which the corresponding Lie algebra lives. Rw are vector spaces defined in this funny way. The intersection of Vn and my Borel upper triangle matrix is transposed in the conjugation by the permutation W, for which this is Rw. So anyway, some kind of vector space. Really, it's sort of the way to think about it is it cuts out from the upper triangle matrices things which are kind of like above and to the right of the inversions of the permutation. That's how you should think of it. And W bar is just W written in the opposite direction. This is a conjugation by the longest element, if you want to do it for general Weil groups. And so there is a lemma we're using, which I might need to explain. So for three permutations, we're assuming that the sum of inversions add up. If they don't add up, just counting degrees of freedom, just like we did with lines, rules out Schubert coefficient being zero. I mean, it is zero unless the sum of the inversion holds. And so we can just assume that. And now the statement says that Schubert coefficient is strictly positive if the sum of vector space is equal to the direct sum of vector space. Okay? That's what Purbu's paper says. Okay? Now, that's a bit of a mouthful, but the way to understand it, this is some rank condition. Rank condition so these vector spaces have a natural basis. And once you understand that, you know what's coming. What's coming is polynomial tensor testing, which again, I'm sort of running fast because I'm not going to explain that. Sounds like you already all know this. But the point is we have polynomials and we're deciding whether it's zero or not. And you can even if polynomials are given to implicitly as a determinant of a large matrix. And now here is what we actually did. What we actually did is we converted this generic condition to be an instance of polynomial tensor testing. So the whole, when I say there is an algorithm, the algorithm is this big. It's one paragraph. It's not that complicated. This could have been done a long time ago. So once you put all the pieces together, so you convert Purbu into PIT and then translate everything, you get the result. This is it's sort of once we wrote it down, it became embarrassingly simple. And what we're saying, I'm gonna finish faster than I expected. So what we're saying is we conjecture that this is the best one can do. So unless you come from a school of people who think PIT can de-randomize, if you don't come from that school, then this is the best one can get. And I'm certainly not in that school. So, I mean, I understand the other opinions. So what we're saying is our upper bound is great. Lower bound we're still working on it. I'm somewhat hopeful. There is a reason I'm writing quasi-polynomial time, because I think it's the right thing to say here. I don't have a next slide, but let me just summarize. From the point of view of combinatorial interpretation, everything was a complete failure. You understand that, right? We proved a great result about vanishing of Schubert coefficients. We essentially understand what's really happening here. But that doesn't rule out existence of combinatorial interpretation of Schubert coefficient. And now that we have that, I don't think Schubert coefficients are actually in Sharp P. I think the conjecture stands. But it's in a complexity class that's low enough that under the randomization it will go into Sharp P. So if you again think RP is the same as P, then probably Schubert coefficients do have a combinatorial interpretation, and then again we got the best we can do. So sorry I finished early. That's it, everybody.
Any questions?
Thank you for the talk. Igor, if I may make a comment, just my intuition is about the Schubert problem has this geometric description. It's really geometric. I mean, it's about intersecting these flags in generic position, and that I think that's intuitively that's the reason why you can have such algorithms, and we don't know of such an interpretation for Kronecker. I mean, we don't see any. I don't see the geometry there.
Correct.
But here I'm not surprised because of, it's intersection theory. So there's geometry. Then you translate it, and actually what you're doing is not really combinatorial. You talk about the subspace.
Now that it's all done, I'm embarrassed to say that I should have come up with that years ago. It's sort of easier to look at the problem. When I started looking at it, I thought it's similar to Kronecker.
One other question or comment, maybe one can reduce the PIE problem to your Schubert positivity.
That's what we're trying to do.
Then you.
So that's right. That's I mean, now that we know what we're talking about, at least a little bit, we can try to do this.
So can you go back to the Pogo result? This is I'm trying to figure out what are the generic objects. I guess there are variables that become variables in PIT. So what are they unitaries?
So the key thing is
sorry, it's not unitary. It's upper. Unit. Okay. So I guess, in a sense, what you explained is that you figure out that this lemma of Pogo is a reduction of Schubert vanishing to PIT.
Yeah, I told you it's this problem goes back to really. I mean, I don't think Schubert stated it this way, but the problem goes back to Hilbert and later Laskushitz and Berger very clearly talked about whether Schubert coefficients are 0 or not. And somehow you needed to understand PIT, that's all you needed to do. I mean,
under this, you called it a lemma. How simple Is it a
Two paragraphs.
translation from-
2 paragraphs. It's really easy.
It's a simple thing from the
Yeah.
definition of Schubert coefficients.
I mean, you have to have an idea, but doesn't use any previous lemmas if that's what you're asking. So slightly unfortunately, I remember I mentioned the way he states and he proves that in a much greater generality than we need. So that's an obstacle for the reader. not mathematical obstacle, but yeah, this is not super hard. You essentially look at this is an argument about the action at the tangent space. That's why you have a Lie algebra. This is not super hard, not at all. And in a perfect world, I would have actually skipped all the HN stuff that I didn't know we're going to have, and would have just given you the proof of the purple. I'm not prepared for that. But no, this is everything is from the book. Everything is really kind of straightforward now that we understand it. I'm a little, before you think it's all done and it's all easy, we don't know if Schubert coefficients are actually computing them. I mean, we don't know if there are sharp Picard. So the analog of Ekenmeyer-Müller-Walter results is completely open for Schubert coefficients. So they not only proved it for vanishing, but for counting as well in unary. So for Schubert coefficient, we spent a long time trying to do this. This would in particular imply that little Richardson coefficients are actually sharp complete in unary, and we don't have tools for that. I don't know how to do that. We spend a lot of time that. So part of my program was to actually show that this is sharp complete, and then you start looking at some polynomials, look at the difference, look at the vanishing. So I've literally written an SF proposal which said what I intend to do, and it's all false. I don't know if NSF is gonna appreciate me proving everything I wanted to do false, but that's what happened.
The slide answered my question.
So I wanted to ask about whether the following notion makes sense to have the sharp L hardness. So sharp L is this complexity class that is inside P, but also kind of counting. And for this problem, is P hardness known or some other hardness already known, or would it make sense to ask for like sharp L hardness?
In this particular problem, I mean, in general, it makes sense, but this particular problem is not. It doesn't. This problem very naturally sits in gap P. Remember, I mentioned before. So it sits in gap P. It's non-negative. So it's a very natural question whether it sits in sharp P. That's so we're really almost splitting hairs. Gap P is almost good enough. It's almost sharp P, and as I mentioned before, we believe it's all sharp P hard. So you really don't want to deal with log space.
And if I understand correctly, we at the moment do not know PIT hardness for this problem.
No. We just started going that direction, to be continued.
What about randomized witness? So witness that you can accept with a randomized computation with a high probability. So something like sharp DPP.
Yes.
Would that still constitute a combinatorial interpretation? Is that
depends?
Because you're counting classical.
I mean, we Googled, and there are basically no papers on that. So whether this would be counted as a combinatorial interpretation, there's a beholder. It's a good question.
aren't any further questions, and thank Igor again.
Thank you.